In this lecture video, let's take a look at how we can actually find the zeros of polynomial functions. So we talk about a lot of things already in the past several lecture videos. So when finding zeros of a polynomial function, if the polynomial function is not easily factorable, just can't factor it, and the graph does not reveal all the zeros, like I cannot find it on the table, then we can actually use a combination of different theorems, concepts, and techniques to actually help us to find all the zeros of polynomial function. So I'm gonna split this particular topic into two videos because there's a lot of different steps. So I don't want to do all four problems at one time. It might kind of take a little bit too long. So let's go ahead and get started. Okay. So here we go. Here is a polynomial function, 2x to the third minus 16. So let's do these questions one at a time. Okay. So let's just call this 1, 2, 3, 4, and this is 4a, 4b, 4c, 4d, maybe c, d, e, right? Okay. 4f, 5, and 6. All right. So let's label them. All right. At most, how many zeros should the polynomial have? So let's look at the degree. Degree is 3. So since degree is 3, so I should have 3 zeros. Okay. Number 2, use a rational zero theorem to list all the possible rational zeros. So my function, 2x to the third minus 16. All right. Rational zero theorem says that do the p over q. All right, let me write the problem down right here. 2x to the third minus 16. All right, if I do the p over q, p got to be the factors of the constant term. Q is the factors of the leading coefficient. So when I do my p over q, what times what is 16? Well, 1 times 16, 2 times 8, and 4 times 4. Just write 1 4 over. Q is 1 times 2. So when I write out my possible rational zeros, okay, 1, 2, 4, 8, 16 over 1 is those exact the same number. All right. 1 over 2 is a half. 2 over 2 is 1. Already got it. 4 over 1 is right here. 4 over 2 is 2. Got it. A over 1 is 8 right here. A over 2 is 4 right there. 16 over 1 is 16. 16 over 2 is 8. So these are the possible rational zeros. The positive ones, so is the negative ones. All right. Number 3, apply the leading term test and sketch one of the 4 scenarios. So this is 2x to the third. So since my leading coefficient, okay, since my leading coefficient is positive and my degree n is 3, which is greater than 0, which one of the 4 scenarios when we talked about on the leading term test should my graph looks like? So my overall graph should look like scribble, scribble, scribble. Okay. It's actually the third scenario. Let me just say third scenario right here. Right side goes up, left side goes down. All right. Number 4. Number 4, there's a lot of parts to number 4. Graph the polynomial function and determine the following. So let's graph it. Because without graphing it, I need to know what's going on by looking at the graph. 2x to the third minus 16. All right, here we go. Standard window. Oh, this is all I see, but I know my graph is supposed to look something like this. Okay, so my graph is probably what? Once it goes up, keep on going up. All right, there's probably going to be at least one turning point. Okay, allow it to keep on going downward. So it's looking something like this. I know that for sure. So first part, how many times did you see the graph cross over the x-axis? Well, by the leading term test, I know once it goes up, once it goes down, it's never going to curve back towards the x-axis again. So all I see is one time. Okay, crossover one time. Oops. For B, what can the possible multiplicity be for the zero that cross over the x-axis? So since I cross over the x-axis, since it's a cross over the x-axis, then the multiplicity will be odd. All right. If it's odd, what can it be? It can be the multiplicity can be 1 or it can be 3. Because as from the previous video, you notice that I can actually have 1 0 with a multiplicity 3. Okay. And then we construct a polynomial function from that. So I can have multiplicity 1 or multiplicity 3. Multiplicity 3 simply means that's the only 0 I have. Multiplicity 1 means, since I only see it cross over one time, the other 2 0 will have to be the non-real zeros. Okay, because those are the one I do not see cross over the x-axis. So how many times did the graph turn at the x-axis? None. So what can the multiplicity be? Can't have any multiplicity. It never turned, so that's none. So I'm sticking with my multiplicity 1 over 3 on that 1 0 I see. All right, now here we go. For E, use the table or the second calc feature to determine the rational zero that crosses or turn at the x-axis. So for E is actually me looking at the rational zero I wrote out, okay, and then actually find it on the table or the second calc feature. Take a look at this number right here. This is a positive. The graph cross over the x-axis at the positive side, so I'm not even worried about none of the negative ones. So table first. Voila, 2. When it cross over at 2, the y is 0. All right. So the 0 that cross over the x-axis is at 2. And that's the only one I see so far. So after determining the rational zeros, 2, what type of zero still remain can be found if there's any. Can the other 2 0? Okay. Can the other 2 0 that I do not see be irrational? No, it cannot be irrational zeros. Irrational zeros are real zeros. Real zero shows up crossing over the x-axis or turn at the x-axis. Since I only see it cross one time, the other 2 can be, the other 2 can be real. Excuse me, can be non-real. All right, what type of zero still remain to be found? Non-real. All right, so if it's non-real, I'm assuming that the multiplicity for that 2 is going to be 1. If the multiplicity is 3, if the actual multiplicity is 3, then the other 2 is actually going to just be another 2, not the non-real ones. So right now, based on what we see so far, you can say, okay, I don't know exactly what my multiplicity is, but I can say the multiplicity is either 1 or 3. If it's 1, then the other 2 got to be non-real. If it's 3, then all 3 my zeros are exactly the same. Now, we don't know that until we go a little bit further. So that's where number 5 comes in. Number 5, use the rational zeros and the multiplicity to perform the synthetic division to break down the polynomial down to a quadratic. This is the reason why we talked about synthetic division and long division before. Because my degree is 3, so I need one rational zero to knock this x to the third down to an x squared. So once I'm down to a quadratic, then I will know what the other 2 zeros are, whether it's going to be non-real or the other 2 is going to still be 2. So let's go ahead and use our synthetic division. So I'm using the 0 that I just found for the synthetic division. Missing terms, 2a to the third plus 0x squared plus 0x, then minus 16. I know my remainder got to be 0 because I know 2 is a 0 to my polynomial function. So if the remainder is not 0, that means we're doing something wrong. All right, bring down the 2. 2 times 2 is 4. We will add, for synthetic division is 4. 2 times 4 is 8. 0 plus 8 is 8. 2 times 8 is positive 16. Synthetic division, if we add, that's a 0. Voila. So right now, this 2, after the synthetic division one time, it knocked my exponent down one at a time. So this 2 actually referring to as 2x squared plus 4x plus 8. Okay. So my quadratic equation that I need to solve is going to be the 2x squared plus 4x plus 8. So from here, if after I solve my quadratic equation, if my answers are still 2 and 2, that means my multiplicity is 3. So that implies that the other 2 0 is actually the same as the 2. It's not the non-real. So this one, step number 6, solving using quadratic formula or the square root property. So let me factor out a 2 first. So that gives me x squared plus 2x plus 4. And you know this trinomial is not factorable. So right away, if it's not factorable, I know the other 2 zeros is not going to be x equal to 2. It's going to be non-real. So let's use our quadratic formula. That will be negative b, which is 2, plus minus square root of my b squared minus 4 times my a times my c, holding over 2 times my a. All right, let's punch it in. Let's see what we got. So that's 2 squared minus 4 times 1 times 4, which is negative 12. So that's going to be negative 2 plus minus square root of negative 12 over 2. So square root of negative is going to be an I. So 4f, the other 2 zeros are non-real. Okay, so let's simplify this a little bit. Let me make this a little bit easier to read. It's all right. I was going to move this up here, but it's all right. Square root of 12 can be breaking down to be square root, that'll be 2 times square root of 3, I believe. Square root of negative going to become I over 2. When all 3 numbers on the outside can be reduced, I will reduce them by 2. So my final answer is going to be negative 1 plus minus square root of 3i. All right, so the other 2 0 got to be negative 1 plus minus square root of 3i. So what are my zeros? So what are my zeros? Let me write it down here. My zeros are, the first one I found was x equal to 2. So that confirms multiplicity got to be 1. Another 0 is negative 1 minus square root of 3i. And the third one going to be negative 1 plus square root of 3i. There you go. Here are my 3 zeros. Okay, go through all this list of things that we learned in order to find my 3 zeros. Okay, so complex conjugated theorem tells me that if my non-real zeros always come in conjugated pairs. One is positive, one is negative. All right, let's try another one. All right, this is a degree is 4, so this is a pretty big one here. All right, so how many zeros should the polynomial function have? So let me just tell you what, let me copy it. Copy this and put it down here. How many zeros should that polynomial have? All right, degree is 4, so I should have 4 zeros. All right. Number 2, let's do the P over Q thing. All right, P got to be the 256. Q got to be the factors of the leading coefficient, which is 1. So when I do the P over Q here, the factors of 1 in the bottom would just be 1. So I just got to figure out the factor of 256. So that will take a little bit of time. So let's try this on the side real quick. 256. All right, 1 times 256. 2 times, let's see, 256 times 2. Excuse me, divided by 2. 128. All right, 3. I don't know. Nope. 4. I gotta find them. Short. 4 times 64. Oh, that's a little bit easier. 5 doesn't go into it. 6. I don't think 6 can go into it either. 7. 7. 7 times 8 is 56, so that's worth a try. Nope. 8. Yep, it will work. 8 and 32. All right. 9, 10, 11, 11. I know 10 can go to 256. Let me try 11. 11, nope. 12. 12 was worth a try. So far, I've been having even numbers. 13, 14, 16. 16 will work. The reason why I know 16 is because I can see that 8 times 2 is 16. Yeah, 16 times 16 will be the last one. All right. So that's 1, 2, 4, 8. 4, 8, 16, 32, 64, 128, and 256. Okay, so they're all going to be over 1. So my P over Q is going to be 1, 2, 4, 8, 16, 32, 64, 128, and 256. So in a minute, when I'm doing after I graph it and do my table, I know I'm not going to have any actual fraction zeros. They're all going to be integers. So easier to find that way. All right, number 3, use a leading term test. So my leading term test tells me my degree upon my leading term is x to the 4th. So my n is 4. My leading coefficient is positive. So one of the 4 scenarios from the leading term test got to be scribble, scribble, scribble. Right side goes up, left side goes up 2. All right, the y-intercept is crazy, okay? It's way up there, positive 256. But as long as we kind of know what the overall graph will look like, I think we're okay. So number 4, let's graph it, and then we'll answer these questions. So x to the 4th plus 16x to the 3rd plus 96x squared plus 256x x plus 256. Okay, let's see what we got. Ooh. That's it. Okay. All right. So we've seen something like this before. What's going on here? This is on the negative side. So I'm thinking about negative, negative 4, negative 8, something like that. I don't know. All right. That's weird looking. Does it turn or did it cross? How many times does the graph actually cross over the x-axis if there's any? Well, we got to look. All right. So apparently negative 2 is right here. 2, 3, 4, 5, 6. I'm going to go from negative 6 to negative 2 in my window just so I can have a better look. What's going on? Oh, that's a turn. Okay. So it turned. Okay. So how many times does a graph actually cross the x-axis? None. So 4b, what should be the multiplicity? None. For C, how many times does it turn? So far, I only see it one time. And what could the multiplicity be? Well, if it's turned, my multiplicity can be 2 or it can be 4. Okay, it cannot be bigger than the degree. So it got to be 2 or 4. All right, for E, use a table to determine the actual rational zero. So I'm going to have the graph up here. I'm going to go to my table. I know it's going to be a negative, and I know I'm not going to have any crazy fraction kind because all my possible rational zeros are integers. Okay, negative 4, 0 is 1. Okay, when the x gets to negative 8, 256. As I keep on going more to the left on my graph, it gets bigger and bigger and bigger. So by the leading term test, I know the graph is not going to curve back. So my actual zero so far is going to be x equal to negative 4. And it has an even multiplicity. So after determining the rational zero, what type of zero are still remain to be found? So I know this. I know my negative 4 got to have an even multiplicity. It can be 2 or 4. If it's 2, then the other 2 0 got to be non-real because I did not see. Okay, I did not see my graph cross over the x-axis anywhere else because the irrational zero shows up on the graphing calculator as a cross. Okay, most of the time it comes in the cross just because it got to come in conjugated pairs, one positive, one negative. So you got to cross it 2 times, which is having odd multiplicity as well. All right, so if I'm assuming my multiplicity is 2, okay, I know so far it's 2. I don't know if it's 2 or 4. I know it's 2, but it can be 4. So if that's the case, I'll have to use this 0 twice to actually go through the synthetic division. So that's the reason why I mentioned the multiplicity on that instruction, because I got to use my negative 4 twice. So let's write out my coefficient. No missing terms. So that's 1, 16, 96, 256, 43210, 256. Okay. All right, let's go through it. First time, 4. This is going to be 20, 80. This is going to be 176. Oh, did I do something wrong? Oh, negative 4. My bad. Oh, man. 0 is negative 4. So that's negative 4. About to say, number got up too quick. Oh, that's 12. That's negative 48. 96 minus 48. 48. Negative 48 times negative 4 is 192. Negative 192. 256 minus 192. 64. And negative 4 times 64 is negative 256. So synthetic division, we will add, so that will be 0. So this 1 right now actually means 1x to the third. Okay? In order to go down quadratic, in order to go down to quadratic, which is x squared, I need to do synthetic division one more time. So since I know my minimum multiplicity on the negative 4 is 2, so that means I will need to use negative 4 again to continue my my synthetic division. So use -4 again, bring down the 1, that's -4, that's +8, this is -32, this is going to be +16, -4 times, -4 times 16 is going to be -64. So my another remainder will be 0. So right now, what I end up with, this 1 actually means 1x squared plus ax plus 16. So the quadratic equation I'm going to solve will be this one. So looking at this, normally step number 6, we use quadratic formula or the square root property if it's only 2 terms. But it turns out, what times what is 16? 4 times 4. This problem is actually factorable. The middle term is going to be +8. So that actually tells me the other 2 zeros is actually going to be still -4. Voila. So this problem, I actually have 4 -4s. Okay, so back to 4f. After determining the rational zero, what type of zero still remain to be found if there is any? So we need to come back and say the other 2 zeros need to be found is actually none. Because the other 2 zeros actually turns out to be exactly the same as the one I found in 4e. Okay, so it turns out my multiplicity for this 0, -4, is actually all 4 of them. Okay, so unfortunately, we do not know this -4 has multiplicity of 4 until we actually solve the other 2 zeros. That's the reason why we still got to go through the process of synthetic division and solving quadratic, just in order for us to come back and say, hey, the multiplicity is actually 4, not 2. Alrighty, so that will conclude this first part of finding the zeros. In the next video, part 2, we will just do the other 2 problems. Okay, thank you for watching.